Recording. So we continue now with part 2 of today's class, and the next topic we're going to talk about is something called precision rectifiers. Now you would remember, because we discussed this and you went through this enough already, that silicon diodes typically need about 0.6, 0.7 volts to be biased to start to conduct. So if you try to rectify a voltage that has an amplitude of less than 0.7 volts typically, you're not going to be able to rectify that. Now, there are many situations where there may be AC voltages, for instance, which are a lot less than 0.7 volts. I keep mentioning things like biomedical signals, for example. Of course, you could take the signal and you can amplify it up to a bigger voltage, and then you work with it. That's one option, and you can use things like the instrumentation amplifier that we had, that we just spoke about. You put that in the circuit, and you could get a gain coming out of it, and then you rectify the voltage coming out. But even in the context of some voltage levels, a 1 volt or 1.5 volt, 0.7 volts is 50% of that. So sometimes there's a requirement to rectify a very small voltage level. And to do that, we use, again, one of these operational amplifiers. It's such a fantastic device, and it's basically, the whole crux of the matter is because the op amp has a lot of feedback inside of it. You remember we mentioned feedback with a power supply, and we'll talk about it more formally in a few weeks' time when we talk about feedback amplifiers. But feedback allows the output of the op amp to, first off, to try to track the input as close as possible. And then the massive gain of the op amp creates that situation where the two inputs try to track each other as well, creating that virtual earth behavior that we spoke about. Because of that, if you put some diodes together with an op amp in a particular way, you can create some devices called precision rectifiers, which are basically diodes like ideal diodes. In other words, they don't need a 0.7 volts to work. And what we basically do with the diodes in these applications is to use them for their other mode of operation, which is that they pass current in one direction and they stop current going in the other way. In other words, like a valve. Yeah. So the first one is, let's look at this particular circuit. All right. Now this circuit here, if you take an operational amplifier, forget the two diodes for the time being. So we have a basic operational amplifier that is wired up as an inverting amplifier. So you ground in non-inverting terminal, and you have an R in and an RF, you have an R and an RF inside of there. And then what you do is to connect two diodes as shown. One diode, D1, is going from the non-inverting input to the output. And then the other diode, D2, is going from the output to the load output. So you're putting D2 between the op amp output and the actual device output that is going to supply the load. All right? So let's see why that works. Let's put a small signal coming in. Right? I'm nominally putting, just for argument's sake, I put a little 0.3 volt sinusoid. So that by itself, if you pass that through a diode, nothing is going to happen. It's not going to be enough to turn on the diode. So you pass that through a diode, you get nothing out. But in this case, because we're passing it through an inverting amplifier, and the gain of the amplifier, remember the behavior of the amplifier is such that as soon as I put a voltage at this point here, as soon as you turn on the amplifier, the voltage here is briefly high, is briefly positive because of that. But because of the op amp behavior and the gain of the op amp, it tries on the virtual earth, it immediately brings this point down to 0 because we're grounded. So within a millisecond of turning on the op amp, it forces that non-inverting input to 0. And the behavior now, because it forces that input to 0, it's also, as an inverting amplifier, is going to try to make VOA negative. Vn is positive, it forces VOA negative, and at the same time brings this one close to 0. So if VOA goes negative because of the inverting amplifier behavior, it means that D1 is off. Sorry, D2 is off. We bring here negative, so we turn off D2. If I turn off D2, then the circuit looks like this. Right? Let me take D2 out of the circuit. So this is what I have. D2 is off, so it basically does not exist in the circuit. VOA is negative because we have an inverting amplifier configuration. And this point here is at 0 volts because here is at 0 volts. So what do we have? The output is disconnected. So one end of RL is at ground. The other end through this chain with RF is also at 0. So no current coming through. So in other words, if Vn is positive, nothing comes out. The circuit ignores that. Fair enough? Yeah? Good. So let's send Vn negative now and see what happens. If I send Vn negative by the same op amp operation that we say, Vn goes negative, VOA here goes positive. If VOA goes positive, here is at 0, so this diode is off. D1, D2, sorry, now turns on. How does that help us? Okay, we look at this thing, and now if D1 is out of the circuit and D2 is in, the circuit basically behaves like a normal inverting amplifier. D2 is now part of the feedback loop. So at this point in time, we have a feedback amplifier, so that the output here is going to be the inverted part of the input. So Vn is negative, and the negative half cycle now, if you follow the current through, if here is 0, remember here is 0, here is gone negative. All right, so if here is negative now, the current flow through here is going to go this way. Here is keeping this thing positive, so here is positive. So the only way the current flow could go is if this point is negative with respect to that point here. So the output conducts. So for the, if you look at the waveform now, if you look at the characteristic, when the input was positive, the output was nothing. When the input is negative, the output is going to track that. So this is what you get. You're getting a precision and inverting half-wave rectifier circuit that is giving me, so if you put a small signal in, you're going to get a half-wave rectified version of the signal coming out. Notice that the only thing that is, the only reason for these diodes in the circuit is that either is to make the circuit connect or disconnect. In one case, this circuit is off, which is here. When D2, when the input here is negative, D2 is out of the circuit, so that the actual output here, this whole thing, basically has nothing flowing through it because you have 0 volts. One side is grounded, the other side is at 0 volts. So we haven't, it has nothing to do with the 0.7 or whether the diode is conducting. All you do is that you reverse bias the diode so it's out of the circuit. Same thing with the other one. When you do this now, when you reverse the process, then you take D1 out of the circuit, and because of that, this circuit now behaves like your normal amplifier. It's an amplifier, but of course we have negative voltages coming in, and because of the behavior of the output here, this has to be positive with respect to that, but this is at ground, so the only way that this could remain forward bias is if here is more negative than here, right? Or here more positive than here, here is more negative than here, or here more positive than here, however you want to put it. This is at 0, so here clearly has to be more negative than it, so the output is a negative voltage at that point. So what you get coming out is that. And remember, I said if I put 0.3 volts here, so this is going to be 0.3 volts here, and you have nothing coming above it. Right, so this is the fancy name for it is an inverting half-wave rectifier, but it is in fact working as a precision half-wave rectifier. So we clear on that? Make sense?
Excuse me, sir, question.
Yeah.
So when we have the negative half cycle, we're basically saying where we have V out, that would be positive, and VOA would be positive as well, because it's inverting.
Right, but what happens is that if you look at what, how is this, let me see how best to explain this here. Because of the presence of the diode, if I took the diode out of this and you had a normal connection, then it would work like a proper inverting amplifier. But because the diode is in, for the diode to be operational, if here, remember here, if RF and RF is in, here has to be more positive than here.
Right.
So if here has to be more positive than here, in terms of a negative voltage, here can't be positive. It has to go below 0 for this diode to be on. So that's why it's actually tracking the negative half of the cycle and not the positive half, just because of the diode.
Okay.
Right?
Okay.
Just look at the behavior of the diode and the fact that the diode has to have the anode more positive than the cathode. So the cathode has to be negative with respect to the anode for it to function. Yeah? So we have a half-wave device. So you could put in that and you could get, right, so the purpose is to switch the output, is to connect the amplifier to the output. This is what I was saying. So depending on what happens, right, the diodes, when one diode is off, the output of the op amp is disconnected from the output of the circuit. And when the other diode is off, the amplifier works in its normal way. Yeah? That's the only purpose. So the diode is not actually doing any rectification work. It's just working like a device that's just switching. So it passes, it connects the circuit or it disconnects the circuit. That's all it's doing. Yeah? So you're getting past the point 0, having to turn on the diode and all that kind of thing. Right? It's as simple as that. All right? So, okay, just give me 1 second. I have to just take a phone call. Yes, apologies for that. I had to take a phone call. These things happen sometimes. All right, so let's go on and have a look at another interesting little circuit here, which is this one. So look at this one, and this one is fairly straightforward. What happens if Vn goes positive? one of these diodes is going to turn on and one is going to turn off. If Vn goes positive, Vn goes positive, what happens to the output of the op amp? Forget the two diodes, if there was just a connection here, right? If Vn goes positive, right, it's an inverting amplifier. So Vn goes positive. So here goes positive, right? Here is 0. This point is 0 volts because of the virtual earth. So if Vn goes positive, this is going to send the output as an inverting amplifier, so the output is going to go negative. If it goes negative, then this diode is off and this diode is on. A negative on the cathode biases cause the diode to turn on. So what's going to happen if Vn goes negative, then whatever happens here, this is supposed to be R as well. Vn goes negative, it appears here. Nothing appears here because D2 is off. Fair enough? So Vn goes negative, it appears as at V out 1. Sorry, Vn goes positive, it appears as V out 1. Vn goes negative, what happens? The reverse. If Vn goes negative, then this point goes positive, D2 turns on, D1 is off, so we get the output appearing here. So if you label it, so Vn positive, let me just label it properly. So in this particular case, very interesting circuit, Vn is positive, it appears here. If Vn is negative, it appears here. Getting a little issue with my thing here. So they call this a signal polarity separator. This might be very useful in certain applications. All right, so for instance, you have signals coming in and think if you want to turn on a particular circuit or you want to do a measurement depending on if the circuit voltage is positive or if it's negative. All right, or you're looking, you have a circuit and this circuit is supposed to be negative all the time, but every so often for some strange reason it goes positive, and you want to keep a track of how much positives and how many negatives of these little variations are happening. Here's a circuit that will take the input and divide it and basically separate the two. So one output will give you, one of the outputs will respond when the input is positive, the other one will respond when the input is negative. Make sense? Very nice application. And here is now a little more complicated one. The first one that we looked at was a half-wave rectifier. But here's another one that we will get a full wave behavior from. So here we have two op amps instead of one. We have the first one, again, we have two diodes connected, DP and DN. We have op amps A and B. All of them are connected together, and the resistances, these three resistances here, 1, 2, and 3, are all the same value. 4 is twice the value of everybody else. Okay, so if these were all 10K, 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 4 would have been 20. All right, and we are sending the input to the non-inverting, we are sending whatever voltage we want to rectify, we're sending it to the non-inverting input of the two op amps. So it's going to both of them together. The inverting of the first one is grounded, the inverting of the second one is connected to a little junction inside of here. All right. Now, one of the things immediately is that we know from the behavior of op amps when you wire it up that the input impedance of the non-inverting configuration is more than the input impedance of the inverting configuration. The input impedance when you have an inverting amp is just simply that first resistor coming in, the R1. Typically, that's because of the gains we normally have like a 10K, 15K, 20K there, so the input impedance is quite low. For the non-inverting amplifier, we are sending the input right into the non-inverting terminal. And typically, if we have the bias resistors around, they're normally a lot higher than that. And the input impedance of the op amp terminals are normally very high anyway. So we're going straight into a high impedance terminal here. Okay, some of this stuff, of course, is back in your notes from 10, 11. So just to read it over when you listen to the lecture again and reviewing, just to refresh your mind on what actually, why I'm saying those things. Okay, so Vn goes positive. Remember, Vn is down at the bottom. And let's see operational. There's a lot of description here, but essentially what happens is that Vn goes positive. If Vn goes positive, then the op amp is a non-inverting amplifier. So if Vn goes positive, this point goes positive. If there goes positive, right, here's also positive. So this also goes. All right, so the input here turns on. Here's also Vn. So all of this point is positive here. DP is on. No current is going to flow through R2. Why is that? In fact, I have no current flowing through R2, R3, and R4. Why is that? Anybody? Right, so let's see what happens here. So DN is reverse bias, correct. So that's the first thing. So DN is reverse bias. So let's take that out of the, because it's reverse bias, there's no connection between the output here and this line here, right? So that's the first thing. Here's at the point here is at Vn approximately. Here is at Vn because of the virtual, oops, In, right, Vn, because of the virtual earth behavior. Here, we have Vn here. So this point here is also at Vn. Okay, so if they have at this point in time Vn at either end of the chain, and that is because this diode is no longer in the circuit Dn. So if they have the same voltage at either end of this chain, then nothing is flowing through here. Okay, no current flowing through here. And then the same thing. So if I have Vn here, no current flowing through here, then of course nothing could be flowing through here as well. So all it's trying to do is the output is a non-inverting amplifier. So the output here will just simply track whatever Vn is at that point. We have nothing else, no current going back here. So this entire bit here, all of this is out of the circuit. Right, so basically you just have the an op amp here connected. This is almost like a voltage follower, in other words, because no current flowing through here. So the voltage out here is following Vn. Yeah, all because Dn is off. Clear up that mess again. Fair enough?
So,
Yeah,
sir, could you run that one more time, please?
Okay, so Vn is positive. Okay, so we said here is positive. it's a non-inverting amplifier, so we're going to have positive here, we have positive here. Okay? Because it's a non-inverting amplifier, again, and because of the virtual earth behavior, we have the same voltage appearing here, and we have the same voltage appearing here. All right? Positive here turns DN off. So there's no connection between this point here and the op amp. Fair enough? So we have V in here. We have V in here. So in other words, there's no voltage drop across our 2 and 3. So now no current is flowing through them. So if no current is flowing through them, remember the op amp B doesn't take any current. So if no current flowing through here, then no current flowing through here as well. All right. In other words, this entire device is operating now just like a voltage follower. Whatever is on the input is going to appear on the output. So this V in positive here, whatever that is going to appear right here. So if V in was positive, we're going to see V in coming on the output here. Yeah?
Yes, thank you, sir.
Well, let's see what happens with V in going negative now. This one is a little trickier. If V in goes negative, then, so this is going, a pen here. This is going negative, here is negative. If that goes negative now, here, the voltage at A goes negative and dP turns off. dP turns off and dN turns on. This now, amplifier A acts like a normal non-inverting amplifier, and the gain will be 1 plus the R2 over R1. Both of them are equal, so it's 1 plus 1 is 2. So you have a gain of 2. We have a minus voltage, we have a voltage of minus V coming in. So with a gain of 2, it means that the potential at point A is minus 2 V in. Yeah? B now is going through, B is operating. Remember that this DN is on and DP is off. So B is now operating. Now this part of the circuit is working. B is operating, and the gain at B now, at this point here, if here is Vn, then B is also at minus Vn, right? Because of the virtual earth behavior here. Make sense? So what is the voltage drop across? We go on here. The voltage, so the potential at A is minus 2V. The potential at B, remember, where are we? The potential at B is, wait a minute, where am I? Let me just backtrack here a little bit. Right, so the potential at A is minus 2VI, and the potential at B is, I'm seeing VI, it should be minus VI. I think it should be minus VI there. Right, a little error inside of there. All right, so just notice that that's supposed to be minus VI. I'll correct that in the notes for you, right? Because if we have negative V in here, this point is supposed to be pulling it to minus V in. Right? So then we can now calculate the current through this as VI over R, because we have minus 2V on one side here, and we have minus V on one side. So we could calculate the current through R3. And then that is the current going through R4, because you remember the op amp itself, op amp B, doesn't take any bias current. So whatever current is passing through R3 is also going to pass through R4. All right? When you work it out now, because of the value of R3 inside of here, you're going to see that the output voltage at R4 is now going to be plus 2VI. Remember, it's an inverting amplifier, a non-inverting amplifier here. Right? But because of the voltage values inside of here, we're going to get 2VI at that point in time. So if the voltage across R4 is 2 VI, and here was at minus VI, minus VI plus 2 VI across here is going to give me plus VI coming at the output here. Fair enough? So let me make sure and correct that. This is supposed to be minus VI here. Yeah? And if that is the case, then again, notice what happened here. We started off with VI positive. When VI was positive, the output V out is also positive. Now, when VI is negative, right, because of the fact that this diode is now conducting and bringing that part of the circuit into behavior. So when the output was positive, the first time we got this behavior here. When the input is negative, we getting this happening. So in other words, we're getting the full wave rectifier. So the output is always positive regardless of what the polarity of the input is, which is your full wave rectifier circuit. And in fact, we call that a high impedance because we're taking the input at the non-inverting inputs here, a high impedance full wave precision rectifier. So you could rectify circuits. Again, remember what the thing is doing. All the precision rectifiers do are to take the diodes and turn them into valves. So they're either in the circuit or out of the circuit. And once they're in this circuit, you could ignore them because we don't care about the voltage across them. All we care about is whether it's connected or not. So if when DN is in the circuit, for instance, let me just clear that up. Right, in the last case that we just did, DP was out of the circuit. So if DP is out of the circuit, all right, DP is out of the circuit here. Right, and DN is in the circuit, then basically what we have is this. Right? So you ignore the diodes, and what we have are just two amplifiers that connected, right? Two non-inverting amplifiers that connected there, and you follow the voltages and the gains as you go through. And in the previous case, right, when the voltage was negative, what happened is that this guy was out, right? So you could kind of get rid of that here, and this one was now connected. So forget the diode. Oops. Forget the diode, and this is what we have. Right? So you have a thing here. This isn't connected. This point isn't connected anywhere. So we have the diode connected here. So this particular amplifier, ignored in the first part, the output goes here and comes out here. In the second case that we had, clear the annotations. Yep. In the second case that we have, okay, as we said, this bit is out, right? And we connect here now. So we have two inverting amplifiers, two non-inverting, I keep saying inverted, two non-inverting amplifiers connected, right? And the output here, basically, it goes from here, it comes out here, it goes back to here, right? Because it's negative, you have a non-inverting, you have a negative here, you have a slightly less negative inside of here, so the current flow is in the opposite direction, which net results that you have a positive, you have a positive voltage appearing at the output here, right? So the input could do this, the output is going to do this. Yeah? Make conceptual sense? Yeah, no, maybe.
So there's a slight little problem with understanding the direction of the current flow and how V out is positive.
Right. Let me see how best. Let me go back to where were we? Okay. So you understand the first part where we were for Vn positive, right? For Vn positive, dp is conducting and dn is out. All right. So just let me see if I could put that here. Right. So dp is conducting and this guy is out here. Okay. So if that is the case, so forget the diode. So at this point in time, dp is conducting. The output of the diode, the output of A is not connected to anywhere. It's just feedback inside of here. Because here and oops, that's not, because this point, let me get a different color. Here and here will be at the same voltage. All right. Remember, Vn is positive. So we have a positive here, we have positive here, we have positive here. Identical values, so no current flowing through this. Yeah? So you have an amplifier. So A is basically out of the thing. Vn is going to be B1, and you have a feedback resistor, but you have nothing connected elsewhere to it. Right? So at that point, this is just acting like a voltage follower. For all intents and purposes, this is the same thing as doing that. Right? It's a voltage follower. So V out is going to follow Vn. Vn is positive, V out is positive. Yeah? Just voltage follower behavior at that point, because the
Right.
rest of the circuit is just off. Right? So amplifier A has nothing to do with it. So we go with Vn negative now. So if Vn is negative, let me just get the and erase the people now. So if Vn is negative, this resistor is out of this circuit. All right, so we could get dp out of this circuit, and we get dn here now. Right. So let's see what we have here now. So Vn is negative. Vn is negative, right? This is a non-inverting amplifier. So what would be the voltage at point A? If it's a non-inverting amplifier, the gain is 1 plus Rf over Rn, right? So because the two of them are equal, that's a gain of 2. So if I have minus something coming in here, I'm going to have minus 2V in here. Yeah?
Understood that, yeah.
Right, okay. So we have B. Now this is going, the same Vn is coming here. So we have minus Vn at this point in time. I have minus Vn coming on this at this point in time. So if here is at 2Vn, A is at 2Vn, here we have, here's at minus Vn. So this point here going up to B, get that thing out of the way, right here should be at minus Vn. Right? Fair enough?
Yes,
So which
sir.
is more positive? Which is more positive? A or B?
B
B is more positive.
B is more
Right. So if
positive.
right, so B is more positive. So that the current, now that the current is flowing inside of here, the current will have to go from the more positive to the negative. Now normal current flows. If the current has to go this way, right, it means V out has to be more positive than VB. Fair enough?
Oh, okay.
V out has to be more positive than V in, and because of the gain of the amplifier here too, what we have is that, oh, here I have a little calculation here. You get that the voltage drop across R4 is 2 V in. So if the voltage at B has to be minus V in, if the voltage here is minus V in, the voltage drop across just because of the current is 2 VI. Here has to be more positive than here. So then here has to be at V in. Right? So that they have the voltage drop of 2 V in across here. So again, the output is positive. So get in. The signal coming in was looking like this. The signal going out now is going to be like this. Or if you draw it on here, it's going to be this, this, right? Which is your full wave rectified behavior. Fair enough?
Fair enough, sir.
Yeah.
Thanks for the explanation. Yeah.
All right. This is kind of like, as I mentioned yesterday too, all of these behaviors are like what, it goes back to something that you learned very early on with op amps when you had the like little Zener diodes and DC sources connected, and you had op amps of various gains, and you're trying to figure out what was the voltage of the output. You know, you have like 2 or 3 of them in cascade, and you have a series of DC, like a battery voltage here or a Zener voltage here or something like that, and the feedback on gong resistors around, and you were asked, okay, so where's the output voltage? It's the same. This is exactly the same behavior. The only thing that we have inside of here now is that we have these 2 diodes. And notice the diodes are doing nothing. They're doing nothing but connecting or disconnecting the op amp to the rest of the circuit. They're not doing any of the rectifying action at all. We don't care that they right, exactly. They just use us, for want of a better word, as electronic valves or switches. Maybe a switch might be a better word, right? So they're either on or they're off. When they bias, they're on, and that means a part of the circuit is connected. When they are not, when they're reverse bias, they are off. That means a part of the circuit is disconnected. So like point A, for instance, if DN is on, point A is connected to resistor R3. If DN is off, point A is just connected back to the input of amplifier A, but nothing else, right? It's not connected anyway. All right. So that's that's why we say that the addition of the diodes to the op amp creates an ideal diode behavior. The diode, it doesn't need 0.7 volts to turn on. The instant you put a voltage, whatever is the minimum input voltage, of course, all the op amps have a minimum voltage in the small millivolt range that it must take before it responds. But as soon as you exceed that minimum voltage, the op amp turns on. The diode just simply decides, once the op amp is turning on, because the diode is there, the op amp works, as I mentioned, right here. The op amp here. Once the op amp turns on, the op amp forces the 2 inputs to be at the same voltage level. And to force the 2 inputs to be at the voltage level, it controls the output. That's what the feedback is being done. So just conceptually, if you wanted to think about the voltage here, for DP to be on, it must have 0.7 volts, right? What the op amp does is when it turns on, in order to make these 2 points equal, it will send the output here 0.7 volts higher than 0. But you don't care about that. It just turns it on and it connects it into the circuit. That's just all you care about, right? It is not making use of the 7 volts. The op amp automatically adjusts because of its behavior to make that diode turn on. But all you have done in the input is just to put in a very small, a small input voltage, far less than 0.7. The op amp turns on, and to force the non-inverting and the inverting inputs to be equal, it will automatically, because of the design of the electronics, it will automatically put the 0.7 volts on the diode to turn it on, to force that to happen. That is what the feedback is about. Okay, and we'll see a little bit more about that in some weeks when we talk about feedback amplifiers. And two, when you see those of you doing signals and systems, when you talk a little about what feedback does, you will see, get an idea conceptually of why that happens. Fair enough? All right, so yesterday and today we bit off quite a chunk of stuff. And the approach, again, I put the circuits up and we spoke about them. We try to analyze it, again, based on the sort of behaviors that we know the op amps are capable of. And the main thing that we address is that the op amps, they either invert or don't invert. Two, that the virtual earth behavior tries to ensure that the input terminals are the same voltage once the op amp is on. The output of the op amp tries to correct the voltages to make that input, the virtual earth behavior occur. And that's where the open loop gain of the op amp comes in. And then the rest is just figuring out when it's working as an inverting amplifier and what's the gain, when it's working as a non-inverting amplifier and what's the gain, and cascade it through from there. Yeah, the circuits themselves, I have to figure out what kind of questions I'll ask you on these kind of things going forward, but I'm putting together some tutorial questions now and to see later on the kind of things that I could probably ask you under exam conditions and so on. Some of the configurations are fairly easy to memorize. So this one, you should be able to memorize. This one, of course, is extremely easy, right? And then the first precision rectifier. All you did was to have the diodes in here. Now, this was an inverting amplifier, so you could think about it. If I were to reverse the diodes, have D1 and D2 connected the next way, what sort of response I would get from the circuit? All right? If I were to take out one of the diodes, there's in fact a precision rectifier with only one diode. How does that work, right? And what's the sort of output waveform for them? All right? So you look at it and you analyze it, think about it. The handout has a lot of the description that we spoke about inside of here. So read it, look at the notes, listen to the class when you get a chance to review, and then come back with the questions if things still not making sense. Yeah? Make sense? Comments? All right. So we push through some work, and the approach is to take the circuits and analyze it. It's a lot easier than trying to design the circuits from scratch. So if I were to ask you, well, you know, how to make a circuit that will rectify a volt less than 0.7 volts, right? That's a lot more difficult. We've come up with this circuit. These circuits exist, so we're more in the analysis mode of it. But now, if you were to be given an application to actually design the thing, and put maybe some values inside of here, that you could draw the circuit and you could put the values and actually plot out what happens. All right. Once you get the multi-sim operating as well, to Mr. Hall is supposed to arrange for those licenses with everybody again. Once you sort out that, then we could simulate some of these things and see if it works the way we think it's supposed to work. All right. And if not, are we wrong or simulation wrong? That kind of thing. Yeah. Right. So if you have the license, then it's sorted and download it, and you could, some of these things you could do the sort of virtual breadboarding, right? So you could put it on the schematic and run the input and see what the output looks like. See if it works. That's the best way to do it. Treat it as a little bit of a virtual lab, and you don't have to you wouldn't blow anything. Right, you're not going to damage any components and that kind of thing, but put it in, wire it up, and see if the thing really works how it is supposed to work, and then we'll talk. Yeah. All right. So if we have no further questions, let me stop recording here.